So we're going to begin now to have a discussion on what is the theory behind a finite wing. So far, all our analysis has been infinite sheets, infinite wings, if you would. Now we have finite because your wing actually has a beginning and has an end. Yes, you're right. This is one wing, this is another wing. But when you talk the airfoil, aircrafts, we consider the whole thing, this two wings, but this is one span, is the whole thing. And one of the things that you have to realize here, because there's a pressure difference, that pressure difference is going to create some vortices here at the end. And this vortex is actually going to create they're going to lower the pressure. So they significantly affect what's your lift in your problem. Okay, and you can see another example here where your airplane is actually taking off, and you can see the vortices that generated around these tips. Okay, so you can think that this is doing something like this. The vortices are being generated. Okay, so in other words, what happens is span-wise, you have a high pressure at the bottom, low pressure top. If this was an infinite, right, it was completely infinite, well, you have no way to do anything else because it's an infinite sheet. But now when it's finite, what happens is you have a high pressure here, but when you come on the tip, what does the high pressure do? And when here's a low? Well, it tends to go up here and tends to take up here. That's what creates this. This motion right here is what creates those vortices that we don't like. Okay? We talked about this before. You got the finite wing is a 3D body that has a beginning and the end. Typically, your lift is way bigger than drag. Has to be, otherwise we don't want to design a problem like that. You have the case of a wing section. That's an airfoil. The span is from tip to tip. The chord is the chord of the wing section. Mid-chord line is when you join the trailing edge with the leading edge. So this is the chord, this is the span, and typically we like to take this in the middle. So we like to say this is, let's say, B over 2, and this direction over here, this is minus B over 2 if we took your Z in this direction, let's say. Okay, so depending on the direction that you take this is how you will do this. We express this. Then the other things you have various cases. Straight wing, when I already talked about this, right? This is straight wing. You can have a case of tapered wing where now you have a sweep angle. Got a sweep angle there. Then the plane area is nothing else than S is equal to B times C. Span is times the chord. The aspect ratio, we talked about this. The mean chord, we also talked about this. The mean chord, again, is the span divided by the aspect ratio. Sometimes you write it like this, but you can also write it AR, no problem with that. Then remember what I told you here at the beginning of our discussion, right? Because of this, it's going to generate some vortices. These vortices force this to actually the tip to go down. Those vortices are actually expressed by these vortices that come here, and they actually are extra velocity that's coming down here. We call that velocity downwash velocity. So you can immediately see that you're going to have the total component of the stream, and then you have a downwash velocity. This is a consequence of a finite wing. If it's infinite, this does not exist, but there's no way of creating this extra extra circulation here. The vortice is there, right? So if we did that, a two-dimensional load case looks like this, but in a three-dimensional, you're going to have this extra small velocity. That's going to be what we call the induced drag. We will talk about that later. And we're going to derive these equations, but in a summary, the drag is a consequence of one of the reasons you got drag is because that induced is because of this downwash velocity. Okay, some airplanes, what they do is they add this, well, you got winglets at the tips. That's just to avoid, if this is coming, pressure is coming up here, it avoids creating this vortex. It's trying to minimize the downwash velocity. So basically, the problem of finite wing, they're not identical to the two-dimensional airfoil, but that assumes there is an infinite case. So what we really want is, we want the lift distribution, the total lift and the total induced drag. The other drag components that are already included, those are standard. We will go over them when we get to the topic. There are 4 theories that we use here, and these theories are the vortex filament. We already discussed this, but in the next lecture we will do a quick summary on this. We had the Biot-Savart law. We Helmholtz vortex theorem, if you remember. That is important, so we're going to compare these two. And the Prandtl's theory, which we haven't talked about, but the final wing theory is based on mainly Prandtl's theory. So that's where we headed for finite wing analysis.